In this class we are going to talk about general relativity, which is a theory of gravity proposed by Albert Einstein in 1915, 10 years after his proposal of a special relativity. Several years before producing the theory of general relativity, he came up and used a principle that we are going to use, as he did, in order to derive many of the consequences of general relativity. And this is the principle of equivalence. And this is principle of equivalence between gravity and a constant acceleration. So as you know, the acceleration produced by gravity is independent of the mass of a body. Namely, if you put in a particular location a body of any mass, because the gravitational force is proportional to the mass, and F equal to ma, mass times acceleration, also contains the mass in the other term of Newton's second law, then the mass of the object drops out and the acceleration is the same independently of the mass of the body. This was already discovered by Galileo Galilei, and he called it the law of falling bodies. And he discovered that close to Earth. He said on Earth all bodies fall with the same acceleration due to gravity independently of their mass. But actually this is true everywhere. So Einstein had a thought that actually he called the happiest thought of his life. And he said, well, gravity, the strength of gravity depends on the observer. So he thought of the following Gedanken experiment, thought experiment. Somebody jumping from a roof would be in free fall, and if he or she leaves something like a piece of chalk while he or she is in free fall, the chalk will also be in free fall, and therefore it would be hovering in front of the person. So in the brief moment before reaching the floor, this person could think that there is no gravity. And actually we have an example of people in free fall in the astronauts. The astronauts that are orbiting around the Earth are in free fall. They are falling towards Earth, but always missing Earth because they move very fast. They are in free fall together with everything else in their spaceship, and therefore they are floating as if there would be no gravity. Now this is exemplified. We're going to see a demonstration that we fittingly call the Einstein Elevator, and consists of a cage in which one can throw out a projectile. So a ball is expelled at a certain velocity. So if the cage is at rest with respect to us on Earth, then the path of this projectile with respect to the cage is the parabolic path that we have seen due to the acceleration of Earth downwards. So how come we can see that this path is parabolic? It deviates from a straight path because there is a sheet of plastic with a hole. And when the cage is at rest, the particle, the projectile, does not pass through the hole. Instead, if the cage is in free fall, at the same moment the projectile is in free fall, then both cage and projectile are falling with the same acceleration, and the path of the projectile then is a straight path with respect to the cage. It goes through the hole, and it can be collected to the other side in a little net that is on the other side. And so a straight path is what we expect if there are no forces. So the projectile path with respect to the cage is as if there would be no gravitational forces whatsoever. And so now we are going to see the demonstration shown by Martin Simon.
This is called Einstein's Elevator, and it's to demonstrate the equivalence between a gravitational field and an acceleration. We have two guns here and here that are aimed in a straight line trajectory to the capture bags over here. And the bullet can only get into those bags if it follows a straight line trajectory from the standpoint of the elevator, somebody inside the elevator. Otherwise, there's a barrier here which will prevent the balls from reaching the capture bags. We can demonstrate that by firing the guns now at rest and see what the effect is. You can see that the balls both hit the barrier because they were falling under the influence of gravity following a parabola. Okay, we've rearmed the guns, put the bullets in. We've set the cage so it can go into free fall. When it's free falling, there's a switch that will trigger the bullets to be fired from the guns. And we'll see what happens this time. 3, 2, 1.
So, as we have just seen, the principle of equivalence is a realization of this idea. So if somebody is hovering seemingly without gravity, it could be that here we see an Einstein is weightless because this spaceship is in the middle of nowhere where gravity is negligible, or the situation from the point of view of the person inside this spaceship is indistinguishable if the person with everything else is in free fall due to whatever gravitational forces are there. So this is the principle of equivalence, right? Free fall and acceleration, constant acceleration, allows to eliminate the acceleration of gravity, and so we are in a situation indistinguishable from having no gravity at all. On the other hand, assume that we are in the middle of nowhere in a spaceship that is being accelerated upwards. Then in this situation, the force that has to be given to the person and everything else upwards in order to produce an acceleration, let us say equal to g, will push everybody up, and so the situation would be indistinguishable if the person is at rest on the surface of a planet like ours, for example, or is just accelerated upwards in the middle of nowhere, since everything would be accelerated in the same fashion. So this is what the principle of equivalence says. So now we are going to draw several conclusions that apply to the situation on the right. So an accelerated spaceship or elevator upwards, and we will apply it to the situation of being on Earth or in the presence of a planet, for example, or large mass. So here it is in the bottom of this page that actually this lady who is in the spaceship could not see the difference between having an accelerated upwards spaceship or being in the surface of the Earth. So from us seeing it from outside, maybe we can distinguish that actually, since there are no forces of gravity in this example, when she lifts this balls that she had in her hand, the balls stay there hovering, but the bottom of this spaceship is coming in an accelerated fashion towards the balls. So from the point of view of this lady, she cannot distinguish if they are the balls that are approaching the bottom of the spaceship in an accelerated fashion because she is on the surface of the Earth and the balls are accelerated, or if the balls stay there and it is the bottom of the spaceship, that actually the floor of this elevator or spaceship, that are approaching the balls. So for an observer accelerated upwards, the body falls just if it would be on Earth. So we can extend then this analogy to other situations. Imagine again that we are in this accelerated vessel moving upwards, and we throw a ball horizontally. So the ball would just go straight, in a straight manner, a straight path. But since the vessel is accelerating upwards, the floor will approach in an accelerated fashion the ball, and therefore we will see the ball as making the parabolic path that is characteristic of projectiles on Earth. Yes, but what is useful about this way of thinking? Well, this way of thinking tells us that if we throw light horizontally instead of throwing a ball, then light will move straight, right, from side to side. However, since the elevator or the spaceship is accelerating upwards, the ray of light will approach the bottom, the floor of this spaceship in an accelerated fashion, in the same way the projectile did. Therefore, applying the same, so since this situation is indistinguishable to the presence on Earth or in any other place where there is gravity, we conclude that light also drops. Namely, light is deflected when passing near a mass as a pebble would, in the same way, except for the fact that light moves at much larger speeds, and therefore we see the deflection less. However, gravitational lensing, which is a consequence of light being deflected by the presence of mass, has been observed. Here you have, for example, a distant quasar, a very bright source, very far away, and the rays of light that should move straight are actually deflected by the presence, in this case, of a cluster of galaxies. And then you see multiple images arriving to us. Here you see multiple images of one particular quasar taken with the space telescope, the Hubble Space Telescope. Here you have another example. If the lensing object is just in the middle, intervening between the observer and the object whose light is being lensed, then the lensing happens all around in the same manner, and there will be a ring formed that is called Einstein Ring. And here you see pictures taken of several Einstein rings. So these are images, modern images taken with modern telescopes, but actually gravitational lensing was what was used to prove the theory of relativity. So it was first observed during a total sun eclipse in 1919. And what was observed was the gravitational lensing or deflection of light due to the presence of the sun of stars that were near the sun.